Hello everyone, in this video we are going to solve exercise 5 for the topic of first order systems. So it has 3 parts A, B, C. For each of the following models, obtain the time response and the time constants. So we want the response of the system in general and not only the steady state response. The first step is to take a Laplace transform of the differential equation that is given to us. We have an initial condition as well, so we have to incorporate that. The initial condition is not 0 or it's not assumed 0, like the way when we find transfer function. So 16 is the coefficient, I keep it, and then I have s, xs, minus the initial condition, plus 14, xs equals 0. I know x0 is 6. So let me rearrange it. 16s plus 14 xs. I have 16 times 6 would be 96. Is a negative 96. I take it to the other side would be positive 96. So xs, which is the response in Laplace domain, would be simply 96 16s plus 14. If I want to take a Laplace inverse, I need to rearrange it so it would be easier for me. I'm trying to rearrange it with the form of s plus a. So in this case, I need to divide everything by this 16, the numerator and denominator. So at the end, for xs, numerator have 6, s plus 14 over 16. If I take a Laplace inverse in time domain, 6 would be the coefficient, e minus 14 over 16 t. And if I want to find the time constant, I compare it with the format of 6e minus t over tau. Tau is a time constant which is in the denominator. So in this case, tau would be 16 over 14. So that is the time constant for me. If we were only interested in the time constant, when we found our fraction here, let me rewrite the fraction. So it would be cleaner. 96 16s plus 14. I could have converted into typical first order format, which is a tau s plus 1, which means that dividing everything by 14. So in that case, xs would have been 96 divided by 14, 16 divided by 14s plus 1. And in that case, I could have directly find the time constant, 16 over 14. Either way, I would get the same value for time constant. But the problem also asks for the response of the system. For part B, we're going to do the same thing. Take a Laplace and then Laplace inverse. So I have 12 s xs minus x naught plus 5xs equals 15 over s. That's a common mistake, to forget to take a Laplace of 15. That value is 3. So I can factor 12s plus 5 xs will give me 15s plus 36. So rearranging it, xs would be 15, s that 12s plus 5 plus 36, 12 plus 5. I can simplify that further. For a common denominator, that would be 15 plus 36s. And if we pay attention to that, you can see that the numerator is just 3 times this parenthesis. So this would be 1, and the whole thing would be 3. So that would be 3 over s. So that would be very easy to transfer it into time domain. That means that it would be 3. So the response of the system is 3. It's a little bit strange to see what that means. Let's plot it. It means it's not a function of time. The response is 3 at all times. It's a constant value. So what is the time constant? The time constant of our system is 0 because it doesn't take any time to reach the steady state. The steady state and the initial state, all of them are the same. So x naught is the same as x infinity is equals 3. So that was an interesting case. Let's do part C. So the same procedure, we have to take a Laplace transform of this differential equation, take an inverse Laplace to find the value. So I have 7, take a Laplace, 7 sxs minus x naught minus 5 xs equals 0. If I factor here, I have xs 7s minus 5 equals, this would be 9. So I have 63 here. Therefore, xs would be 63, 7s minus 5. I can rearrange this. So xs, I divide everything by 7. So I get to my easy format for Laplace inverse. Therefore, it's very easy to take a Laplace inverse of this. It would be 9e. Remember, this one is negative 5 over 7. So here I have positive 5 over 7t. So that's the response of my system. So what would be the tau value? Again, if you want to compare it to the first order system, a, e, negative t over tau, you would see tau would be negative 7 over 5. A negative time constant, so that's a negative 7 over 5 second. We don't have a negative time. Let's plot this to see what it looks like. At x0 we have 9, and then it just goes up. So this system is unstable. So time constant is not defined for this system. So the system is unstable. So the time constant is not defined. And if you look at the poles of the system, s minus 5 over 7, that means that the pole, we have one pole here is positive. A positive pole indicates an unstable system. You have a positive pole here. If this is j omega, any pole on the right side of j omega will cause our system to be unstable. And that's why we are not going to reach a steady state response, because our system grows